You know, we all remember the quadratic formula from school, right? It's that trusty, powerful tool for cracking any equation that looks like ax squared plus bx plus c equals 0. But what if I told you that this formula we all memorized has a secret, a hidden dimension that opens up a whole new universe of numbers, one that most of us just flew right past in class?
So let's get right to the heart of the mystery. We're taught that the solutions, the roots, are simply the points where the parabola hits the x-axis. Simple enough. But then, you see a graph like this. This parabola is just floating. It never touches the axis at all. So what does that mean? No solution? Or are the answers hiding somewhere we can't see?
Okay, so just a super quick refresher. A quadratic equation is anything that fits this standard form. When we say we're solving it, we're really just on a hunt for the values of x, the roots, that make the whole thing balance out to 0.
And this is where the algebra beautifully connects with the geometry. Those roots we calculate are the exact spots where the parabola physically crosses that horizontal x-axis. It's a clean, perfect relationship. Except when it's not. This is the very connection that seems to completely fall apart with our floating parabola.
And that brings us right to the core of it. What is the quadratic formula trying to tell us when the picture doesn't match our expectations? When there are no x-intercepts to point to, where do we go from there?
Well, the key to this whole thing is actually hiding inside the formula itself. It's that little chunk under the square root sign, b squared minus 4ac. This has a special name, the discriminant. And it's basically a crystal ball that tells you exactly what kind of answer you're about to get. And it really all boils down to 3 possibilities. If the discriminant is positive, great. You get 2 different real roots, 2 crossing points. If it's 0, you get 1 real root. That's when the parabola's tip just kisses the axis. But when it's negative, the formula tells us we're getting 2 complex roots. And that's our floating parabola situation.
Now, this is the point where a lot of us were taught to just stop. You see a negative under the square root and you think, well, that's impossible, no solution. But that is a huge misconception. No real solutions does not mean no solutions at all. It just means the answers aren't on the number line we're used to.
So, how did mathematicians get around this? Well, they didn't just stumble upon some forgotten rule. They did something way more brilliant, way more creative. They invented a brand new kind of number.
They asked a really bold, almost rebellious question. For centuries, everyone agreed taking the square root of a negative was impossible. It was a mathematical dead end. But they asked, what if it wasn't? What if we just defined our way out of the problem?
And boom, this is it. The imaginary unit, called I. It's an entire concept built on one simple, powerful idea. I is the number that, when you square it, you get -1. And with that one elegant invention, a whole world of impossible math suddenly snapped into focus.
And that's the big mental shift right there. A negative discriminant is no longer an error message. It's not a dead end. Think of it like a signpost, pointing us off the familiar road of the real number line and into a whole new dimension, the world of complex numbers.
Okay, so we've got this incredible new tool, I, but how do we actually use it to solve the mystery of our floating parabola? Let's walk through it step by step.
The great news is the process is pretty much the one you already know. You find your a, b, and c, you plug them into the formula. The only new trick is in step 3. When you hit that negative under the square root, say the square root of -16, you just split it up. It becomes the square root of 16 times the square root of -1, which is just 4i. Simple as that.
And this process gives you answers that look like this. A plus b. This is a complex number. It's got 2 parts. There's a real part, a, that lives on that good old number line we know and love, and then there's an imaginary part, bi, that exists in that new dimension that I unlocked for us. Now here's where it gets really cool. These complex roots, they never show up alone. There's this rule called the complex conjugate root theorem, which basically says that if a plus bi is a solution, then its perfect mirror image, a minus bi, has to be a solution too. They always come in pairs.
And you can just see the beautiful symmetry here, right? The real part, the 3 or the -1, stays exactly the same, but the imaginary part is a perfect reflection. One is plus, the other is minus. It's this unbreakable partnership. All right, so we have these invisible, abstract solutions, but we started with a picture, a graph. So the big question is, can we actually see these complex numbers on our graph?
The answer is a resounding yes. You just have to know how to look.
Here's the trick, and it's so clever. You take our original floating parabola, and you imagine a mirror placed on the horizontal line that just barely touches its lowest point, its vertex. Then you just reflect it.
This reflected parabola, we can call it an auxiliary polynomial, is now the mirror image of our original. It shares the exact same vertex, but now it opens downwards. And look, unlike our original, this new one definitely crosses the x-axis.
And right here, this is where it all comes together. Those 2 points where our reflected parabola crosses the axis hold the secret. The exact midpoint between them, that's the real part of your complex solution. And the distance from that midpoint out to one of the crossing points, that gives you the imaginary part. It's all been right there on the graph the whole time.
So what this brilliantly shows us is that complex roots aren't just some abstract algebraic trick, they are physically, geometrically tied to the very shape of the parabola itself. They weren't missing, they were just hiding in its symmetry and its reflection. And honestly, this is just scratching the surface. Imaginary numbers are absolutely essential for things like electrical engineering, quantum mechanics, signal processing, fields that shape our modern world. It really makes you wonder, doesn't it? What other huge breakthroughs are just sitting there, waiting for us, hidden inside a problem we think we already have all the answers to?